When looking out at the universe at the largest scales using sophisticated telescopes like this one here, one thing becomes quite evident: things are surprisingly simple and straightforward. When we peer into our world using the Large Hadron Collider, we find that even at the tiniest scales, everything aligns with established physics, no surprises. Yet, it's a strikingly orderly cosmos out there, from the colossal to the small. Whether you're gazing at the stars or peering into the heart of matter, scientists thought that two big ideas would explain everything. One is called string theory, a massively intricate mathematical framework that, for all its flair, hasn't actually solved any major questions yet. The other is cosmic inflation, which suggests that the universe suddenly expanded faster than the speed of light for a fraction of a second. But we aren't really sure what came before inflation or what powered it. However, together these two ideas suggest that the universe is super complicated when you look closely and very chaotic from a macro perspective. That does not coincide with observations on the largest cosmic scales. The universe is both homogeneous and isotropic. This means that no matter where you are in the universe or in which direction you look, the universe appears largely the same. So, either the universe's apparent simplicity might just be due to the limited range of scales we can currently observe, or maybe as we explore scales much larger or smaller, the anticipated complexity that our theories suggest may eventually come to light. Or maybe the universe really is as simple and predictable as it looks from its grand scale to the tiniest particles. And if that is true, the clues to cracking some of the universe's biggest mysteries might already be hiding in plain sight, waiting for us to connect the dots. But what if the answer lies not in our universe, but in another? Welcome to territory. This is your space. Haven't you ever heard of Occam's razor? The simplest explanation is probably the correct one. In the world of scientific reasoning, there's an effective principle known as Occam's razor. Suppose astronomers observe unexplained lights on another planet. Instead of concluding aliens are there, Occam's razor asks them to consider simpler causes first, like atmospheric conditions or natural planetary phenomena. But why bring up Occam's factor here? Well, many inflation models suggest that the rapid expansion of the early universe should have created long-wavelength gravitational waves, basically ripples in space-time. Detecting these waves would provide strong confirmation of inflation. Now, to be clear, scientists have detected gravitational waves, but coming from events like merging black holes and neutron stars. And despite many sensitive searches, no signs of these primordial waves have been found, with each new experiment ruling out more inflation models. While the inflation theory does explain some issues, like why the universe looks so uniform on a large scale, it also introduces new challenges, like what energy field actually powered inflation. Inflation requires the universe to have very specific initial conditions, but why were these conditions present to begin with? Some inflation models suggest infinite bubble universes. This raises philosophical and scientific questions about testability and the nature of physical reality. So ignoring the Occam factor here would be basically assuming that there are no simpler explanations. That is something Neil Turok, the Higgs Chair of Theoretical Physics, set out to change. Together with his colleague, Lee M. Bohl, Turok approached a new theoretical model that could address fundamental cosmic questions without relying on traditional inflation and string theory. If we use Einstein's theory of general relativity and the known laws of physics to follow the universe backward in time, we arrive at a point where space and time shrink to a single point called the initial singularity. To make sense of the extremely dense, hot state at the beginning of the universe, theorists like Nobel laureate Roger Penrose identified a key symmetry in the laws of light and massless particles. This symmetry, called conformal symmetry, suggests that neither light nor massless particles experience the usual shrinking of space at the Big Bang, allowing them to bypass the intense conditions that otherwise affect all other forms of matter. Imagine you have a stretchy rubber sheet, like a rubber band with a drawing on it. Now, if you pull or squish that rubber sheet, You might change the size of the drawing, but you're not changing the shape of the things in the drawing. Conformal symmetry implies that the universe could have a similar structure, remaining unchanged no matter how you scale it. This property could mean that rather than being shaped by an explosive event like inflation, the universe's evenness might arise naturally from this symmetry. They proposed that the initial singularity, instead of being a one-way origin, acts like a mirror in time. On one side, time flows forward, on the other, it flows backward like a cosmic reflection. This mirror at the Big Bang aligns with the idea that every physical process has a mirror counterpart, where space-time and particles are reversed, thus following Captain symmetry, a fundamental balance in nature. Imagine the universe as a grand stage, where particles act out a play. In this play, three special rules: charge, parity, and time govern how things behave. Charge is like swapping matter for antimatter. Parity flips the scene, as if you're looking in a mirror, and time is running the play backward. Now, if you change all three at once, flip charges, mirror everything, and run time backward, the laws of physics stay perfectly unchanged. The universe doesn't break a sweat. It still plays by the same rules, like a well-rehearsed performance, no matter how you rearrange it. Yet the apparent dominance of particles over antiparticles and the unidirectional flow of time in our universe make it seem that Captain symmetry might be violated. The mirror universe concept, however, reinstates this symmetry by suggesting that our universe has a reversed mirror counterpart. In this mirror reality, time moves backward and antiparticles outnumber particles. This parallel universe need not be a real place but could be a mathematical construct to explain symmetry at the universe's origin. Their theory also sheds light on dark matter. Neutrinos, which are like particles moving near light speed, spin in a left-handed orientation. However, heavy right-hand neutrinos predicted to be stable are possible dark matter candidates, as they interact only through gravity. Using their mirror hypothesis, Turok and Bohl calculated that these right-hand neutrinos could indeed account for dark matter. Basically, the theory suggests that if dark matter is made of heavy right-hand neutrinos, then out of the three types of known light neutrinos, at least one would have to have zero mass. This prediction is being tested by studying how galaxies and other cosmic structures are arranged in space. Observing how matter clumps together across the universe might reveal clues about neutrino mass, helping to confirm or refute this theory about dark matter. The scientists also tackled the mystery of why the universe appears flat and uniform on large scales. They explained this using the concept of entropy, which helps describe how likely certain configurations are. They discovered that a flat, rapidly expanding universe with a small positive acceleration is the most probable state. Additionally, they showed that density variations, usually linked to inflation, could actually be explained through quantum fields. However, more research is needed to ensure the new theory holds up scientifically. Picturing the Big Bang as a mirror neatly explains many features of the universe which might otherwise appear to conflict with the most basic laws of physics, wrote Turok, who published his team's findings in the journal Annals of Physics. The progress we have made convinces me that, in all likelihood, there are alternatives to the standard orthodoxy which has become a straitjacket we need to break out of. While much more work is needed to support this fascinating idea, Turok suggests that even if proven wrong, it highlights the possibility of simpler explanations than those provided by the standard model. What do you guys think? Let me know by dropping in your comments below. And as always, don't forget to subscribe to Territory because this is your space.